In the previous video, we talked about curvatures of curves. Now we're going to generalize that to talk about curvature of surfaces in space. In this video, we're just going to give some intuition. The formal treatment will be discussed in subsequent videos. So let's say we have a nice surface in space and we fix a unit normal vector field n. Okay. Now, let P be a point on our surface, and we want to define the notion of curvature at P. Now, observe the first problem we have is that the surface might curve differently in different directions at P. For example, let's look at this picture. We can think of this as a folded piece of paper. Then at this point P, in this direction, the surface is flat. There's no curving. However, in this direction, the surface is curved. So it makes more sense to associate a curvature for each direction at P. A natural idea is as follows. So for every direction V here, we might associate the following curvature. We can look at the plane, the normal plane to our manifold, going through P, and it's in the direction of V. This plane is going to intersect the manifold in a curve. We can call this a normal section of our surface. Note that V is going to be the velocity vector of this curve at P. It's going to be tangent to this curve at P. Now, this is a plane curve, so we do have a well-defined notion of curvature. Actually, we can even use the notion of sine curvature because we have a fixed normal vector here. So we can just define this curvature in this direction to be the sine curvature at P of this normal section. The max and the min value of these curvature, if exist, are called the principal curvatures. Okay, but they are not intrinsic. For example, the surface that I drew before is isometric to the plane. We can think of this as being obtained from the plane by bending it, by folding without creating sharp corner. Now observe that the principal curvatures are not preserved under this isometry. Why is that? Because first of all, at any point on the plane, the curvature in all directions must be 0. Right? The plane is flat in all directions. However, here, at this point here on this surface, we see that. So let's see what the principal curvatures are here. So the one direction is 0, this is good, but the other principal curvature corresponds to the curvature of this curve, this green curve here, and that's clearly non-zero. So it was not preserved under this isometry. However, it turns out that the product of these principal curvatures is gonna be intrinsic. It's gonna be preserved under isometry. We call this the Gaussian curvature.